Hey guys, in this video we're going to be reviewing logistics and Euler's method. I'm coming to you from my basement. I plan on doing these from all different rooms in my house so you'll get to know me and my surroundings very well. Do a little slow turn. I've got the fire going. What else do I have? I've got the backyard with the pond, my husband's workspace right now, the downstairs kitchen, and a closet filled with, you guessed it, toilet paper. Awesome. Good to see you guys. So on a blank sheet of paper, we're going to take some notes on logistics and just a quick review, see how it goes. I've got my trusty iPad going here, and I'll do my best. You can see I did my hair today. Looking lovely. It's one good thing, I guess. I don't have to fix my hair. Always look on the bright side, kids, right? So let's go talk about our logistics model. Remember the graph, kind of appropriate right now. You've probably seen this graph a bunch lately, huh? Sorry about that little fleck. I had a piece of a chip on my screen. All right, so we have a population of something or an amount, bacteria, people, whatever. We call that Y of 0 or P of 0 or C of 0 or whatever. And it grows at an increasing rate, reaching a maximum growth rate, and then grows but at a decreasing rate on out to infinity. This amount that it doesn't surpass, this horizontal asymptote up here, is located at what we call L for the carrying capacity. So we have a limit that goes with this, but first of all, let's revisit what the differential equation looks like for logistics growth. The rate of change of a population over time is directly proportional to the amount and the difference between that amount and the carrying capacity. So I guess at this time, the coronavirus would be a good thing to reference right here, although we're probably getting sick of hearing of it, but this would be the rate that the virus, or number of people who have the virus is growing over time, is directly proportional to those who have it, and this would be in the product of those who don't have it. So L would be the maximum of the population, or at least the maximum amount of people who can get it. So a couple things that happen right here. My limit as t, again this is my t-axis, approaches infinity of y is equal to L. So the limit of that carrying capacity, to actually be y as a function of time, is L. The limit as t approaches infinity of the rate of change is equal to 0. And this one's really helpful for when they mess with the models. And you guys are pretty good at this when we did it, so shouldn't be a huge issue for us. So let's see what else we need to have on here. We know that at that inflection point, right here, is when there's a maximum growth rate. So dy dt is at a max. That's when it's growing the most rapidly. Keep in mind with that coronavirus, they wanted it to look like this. They've been talking about flattening the curve. We're getting that bell curve to go down. If you missed that window of opportunity, we head on out to the carrying capacity. And interestingly enough, the governor stated yesterday that he believes that Minnesota had missed their opportunity to flatten that bell curve. So now we are just trying to make sure we don't infiltrate or overburden our medical system, because we're kind of heading like this, albeit slowly. Not to worry, because most everybody recovers, but just so you get the math behind it, the goal was to flatten that curve. So now let's go take a look at, it's very appropriate right now, isn't it? Let's go talk about some other stuff we know. That maximum growth rate will occur at half the carrying capacity. And let's talk about what this is here, would be the point 0, y of 0. How many people have it at the start of our investigations? On this piece of the curve, we'd say that y is increasing at an increasing rate. Over here, y is increasing at a decreasing rate. So dy dt is positive for all t, right? It's just the second derivative is what's different. When we increase at an increasing rate on the first part of the curve, that would be right here, we're concave up, right? So d squared y dx squared is greater than 0 on that first part of the curve where it's concave up. And likewise, it's less than 0 on the second part of the curve where we're concave down. What else do we need to know? It's possible to come in from above your carrying capacity. That would be, like I said, I think when we did this, if you put a certain amount of fish, you just dumped them in a fish tank and it couldn't support, they're just going to die off until they reach their carrying capacity. So if we come in from above the carrying capacity, you'll notice that it decreases at a decreasing rate. Interesting, right? So let's go take a look at our different forms. So we have this differential equation, dy dt, and I told you to remember Kylie. But remember, this y generally gets changed to something else, like the rate that bacteria is spreading over time is directly proportional to the amount of bacteria and the amount of space left in the population. So remember, this one, it's Kylie, but it's whatever's on top of that goes in there. So there's other forms that this can be in. So remember, it's really important. It's helpful to just kind of think of that its limit as t approaches infinity goes to 0. So that's pretty helpful. But sometimes this gets distributed in, and you'll see it as some constant times y. It's actually k times L. So I'm going to put some other constant times y minus ky squared. So sometimes you'll see it in this form. But again, if you factor out that y and find where it's 0, that will give you the carrying capacity. So that's kind of nice. Sometimes, I'm going to go shoot off over this way. Sometimes what it looks like is we take, sorry, it's getting a little messy, but I'm doing my best here. Sometimes what they'll do is they'll divide this by L. And when doing that, it upsets it, so I have to multiply by L. So what we'll do is we'll see some other constant. It's actually the combination of the carrying capacity and the constant of proportionality times y out front. So you might see like a 0.01y times 1, L over L, minus y over L. So remember, this would be 0 when y equals L, and that's when we're at the carrying capacity. And we'll go do an example so you can, but I think you remember that. So the next thing I wanted to do is talk about the format for Euler's method, and then we'll go do an example of each of these. Just a quick little review of 2 topics that I know you'll be tested on, right? So for Euler's method, just kind of keep in mind what Euler's does, right? We did the tangent line approximations in Calc AB. We use a tangent line to approximate what happens on the curve. Remember, there's error unless we stay really close to that point of tangency. What Euler's method does is it says, okay, you know, let's stay on that tangent line for a while, but then stop and adjust the slope, and then stop and adjust the slope, and then and it sort of like walks it along a tightrope of these little tiny toothpicks that we keep turning as we move along the curve. Even better yet are our Taylor polynomials that we're currently just finishing up, because those allow us to maybe hug a cubic to it or something, and boy, that looks pretty good for a little while, right? So we have 3 ways right now of approximating what happens on a function using other math models. For Euler's method, what we need is a starting point. So remember, we made a table when we did these, so I just want to bring back the table, but you really don't need to memorize it if you understand that you're hopping on at the point given. I'm just going to call that the point. So you hop on at some point. Let's call it x sub 0, y sub 0. That'd be like right here if they say hop on at the point 1, comma 1. All right? Then what we do is we calculate the slope there. That'll be given as a differential equation. So maybe the slope right here at first was, I don't know, it's pretty steep, a half. They'll tell us how far to step over. So we have what's called a step size, which means move over right? But when you move over, you have to move up. So we're going to move over, we're going to move up. And remember, to get the delta y is equal to the slope times the change in x. So we just multiply these two in this column. And then we end up at our new point. Remember, our new point would have been our old one plus the change in the x value, and then our old y plus the change in the y value. So these are the mechanics needed to make Euler's work. It was easy, not a huge deal. So hopefully you printed off the PDF that I had in Schoology that goes with this, and let's go take a look at, I went the wrong way, two problems that I want to do. This one, I didn't write this actually, it was on the internet. It's a little bit old, I downloaded it, I don't know, a couple weeks ago, so the data is probably not very accurate. I don't even know if it was originally, I just found it. But let's go take a look at what we have here. And you'll need a calculator for this one. So while you're getting yours, I'm gonna go grab mine. I have one right over here. So go grab a calculator, pause this, and let's go do a full, would you ever have a full logistics FRQ? No, but this one's fake. It says the number of people N infected with COVID-19 in China increases at a rate described by the logistics model below. Notice this does look logistics-y, right? It's got that Kylie sort of, and you might say, well, not really, but it is. It's that one where they've divided. Excuse me, I burped. I apologize. Excuse me. Anyway, it says initial condition. Perfect. It says ultimately how many people will be infected. So for part A, it's asking you for the carrying capacity, which we call the L. Remember, the rate of change at the carrying capacity, right? As t approaches infinity, that rate of change, limit as t approaches infinity of that rate of change is equal to 0. So we have to figure out, well, when will our rate of change be 0? Keep in mind what that means. It's starting and it's flattening out. That slope of that tangent line is approaching 0. So it's either at n equals 0, which doesn't make sense because that's no people, or we're 1 minus n over 80,791. So you can easily see. So if you just understand that that rate of change equals 0 at the carrying capacity, that's pretty helpful. My carrying capacity is 80,791 just because I understand the model. For what value of n is the number of people infected in China growing the fastest? Well, that's at this inflection point. We proved when we did this chapter that it happens at half the carrying capacity. If you remember, the proof for it involved finding the inflection point, setting a second derivative equal to 0, but I'm not going to revisit that. I'm not teaching the lesson, we're just remembering. So I'd have 80,791 divided by 2. So let's go do that on our calculator. 80,791 divided by 2, 40395.5. So let's round down on this one since it's number of people. I want to have a half of a person. So at that many people, we'll say. Part C says to solve the differential equation. That's almost never asked on the AP test. I'll eat my shoe if you get asked to solve the logistics DiffEq. But if so, you should smoothly move into it because remember what we said, that when dy dt is equal to ky times L minus y, right? What we know is that the solution, and you can go back and look in your notes, but we found it by separating and integrating and all that good stuff and antiderivatives. But when we are all done, we got lice minus licked. All right, so for mine, because it was dn dt, right, we're still going to have n as a function of t is equal to the carrying capacity over 1 plus an unknown, e to the negative L, I know it, 80,791, k, I know it. You might say, no, we don't. Yeah, we do. Remember, it's ky times L minus Y. So I can figure that K out pretty easily. Here's what I would do. I'm going to go back up to that one. So it's in the form KY times L minus Y. So what I'm going to need to do for this one is take that carrying capacity, right? That 80,791, multiply it by it. So I'll have L minus Y. But then I need to divide this by it to get the K. So really, you know, it wasn't quite in the right format. So we need to divide. Boy, that's going to be a really small number there for my K. It's going to be 0.22556 divided by 80,791. So we've got about 2.8 times 10 to the negative 6th. So I'm just going to store that and write K. 2.8 times 10 to the negative 6. I'm going to hit store, and I'll hit alpha K. Let's store that sucker in, where's my K? K. All right, I should actually have a calculator going here too, but you guys know what you're doing, right? So next up, let's go back to our model, right? We have our K stored, and C is what we're going to need to find. All right, so this is KT. So that's where that initial condition comes into play, that when T is 0, we get a 191 out of our model. So 191 has to equal 80,791 over 1 plus CE to the negative 80,000. You can see why you won't have to solve one of these on the AP test, but I kind of like it. K times 0, right? Now, all of this is going to go to 1. So when I solve this for C, I'd multiply by 1 plus C, and then I divide by 191, and then subtract 1. So 80,791 divided by 191 equals, and then I'll subtract off 1, and I'm at about 400, let's just say 422. C equals 422. All right. Back to my model. I didn't know this one was going to be so long. I apologize. Sorry, guys. Well, not really. It's good. Not like you've been doing a whole lot the last couple weeks, right? We can do a hard logistics model problem. So I'm going to go back here. I'm going to write my final model down. So the number of people infected in China at any given time t is equal to the carrying capacity over 1 plus the C I just found, 422 e to the negative L stored in KK, right? T. All right, there's my model. The question was, what value of the time t corresponds to the value of n obtained from part B? So basically, they want to know at what time will the number of people infected be growing the fastest? Remember, we said that occurs when we're at half the carrying capacity. So when we were at half that carrying capacity, which was 80,791 divided by 2, and we said we're going to use 40,395. That's what we're trying to figure out at what time. So we have 80,791 over 1 plus 422. This is cool stuff. You should show your parents. I'm going to move this out of the way here. Sorry. I don't want to erase the whole screen. I just want to erase parts of the screen. All right, so 80,791 over 1 plus 422 E. E, why won't it write? Because I have it on the eraser, ding dong. E. E. There we go. To the negative L. I'm getting sick of this problem, but I like it. Pardon the pun. K, which is stored, t. So let's go solve this sucker. How are we going to do that? We're on the t attack, right? Let's get it out of the denominator. So to get it out of the denominator, I will multiply by it. So I'll have 1 plus 422e to the negative. And if you don't mind, I'm just going to write LKT because I don't want to write those numbers in. Will equal 80,791 divided by, what's going to equal 2? Duh, because I took half the carrying capacity. So that's kind of nice. 2. So 422e to the negative LKT equals 2 over 422. No, it doesn't. It equals, now I'm getting sloppy, equals 1, right? Yes. Next up, natural log, natural log. So negative LKT is equal to natural log of 1 over 422. So t is going to equal the natural log of 1 over 422 divided by negative LK. Let's hope this works on my calculator. Wish us luck. I didn't do this ahead of time, so you're getting it on the fly here. 1 divided by 422, the natural log of, divided by negative L in parentheses, that's negative 80,791 times stored in K, so alpha K equals 26.5-ish. I don't know if that's right. I think it is, unless I made an arithmetic mistake, days. Wow, that was crazy, huh? Will you have to do one like that? No, but we like to practice harder than we're going to play. Usually what happens with these is you're just asked to interpret the model of some sort. Like it'll say the rate the rumor is spreading over time is directly proportional to the people who heard the rumor, and there might be a number in here, 0.03, times 200 minus that. My pen's not working. Oh, dang it. I'm sorry. And that might ask you, well, what's the carrying capacity? Well, remember that rate of change at the carrying capacity approaches 0. So my carrying capacity is 210. Those are just too easy. So I decided I'd do a hard one. Answer, 26.5 days, and it's applicable too. You're welcome. All right. Let's go take a look at this one. We're not going to do the first 2 parts of it because that's not what I'm reviewing today. Let's go look at our Euler's method. All right, so for Euler's method, how about I get my, I was going to get my face out of there. I forget that I'm on there. So anyway, Euler's method, let y equal f of x be a particular solution to the differential equation with the initial conditions, yada, yada, yada. Use Euler's method. What does that tell me to do? Start my table. I am hopping on the unknown curve at 0, -2. I will find the slope there. How do I do that? I plug 0, -2 into my diffie q. So I would do 3 times the x plus 2 times the y plus 1. That's going to give me a -3. Then what will I do? I'm going to scoot over. How do I figure that out? Well, it says I'm supposed to start at 0 with a step size of 1/2. They handed it to me. Thank you very much. Then I need to know, well, how far up do I go? The slope times the change in x is equal to the change in y. That's our dy dx, right? So my change in y will equal the product of those two, which is -1/2 or -3/2. I don't know if you like fractions or decimals. I think fractions are my friends. A new point, right? So where will I be after I've walked along that little tightrope? I'll have scooted over 1/2 because I was at 0. And then I have a delta x of 1/2. I was at -2, but then I went back -3/2. So that'd be -3.5 or -7/2 I like. All right, now I'm going to hop on the curve. Where am I now? I've moved over to a half, and I'm at -7/2. So what do? I find the slope there. I'm adjusting my slope as I walk along the curve. My slope there will be 3 times the x, 3/2, right? Plus 2 times the y, so that's going to be -7 when I double that, and then plus 1. Let's get a common denominator there. Sorry, I feel like I have to sneeze. 3/2 minus 14/2 plus 2/2. So it looks like I'm at -9/2. Arithmetic, and delta x, I'm just going to move over. I multiply these, I get a -9/4, right? And then what's my new point going to be? I'm at a half. I scooted over a half. I'm now at 1. I was at -7/2 and I moved back 9/4 or down. So -7/2 minus 9/4 would be 14/4. So -23/4 or -5 3/4 is my approximate for f of 1. And again, I'm not on the curve. Keep in mind what those approximations are. I'm not on the curve there, but actually, it's been going like this maybe, but I'm on this little tangent line that's approximating it, and I'm going to be a little off. All right, letter D, last one up. This one had in this year, I think this was 2007, it had a double dipper on the Euler's method. So if you didn't know how to do it, you kind of lost a lot on this FRQ. Usually it's just a singular question on an FRQ. Oh, I'm getting uncomfortable. So let y equal g of x be some other solution to the differential equation with initial condition 0k. So I'm hopping on at 0, I don't know, where k is a constant. We're going to use Euler's method starting at 0 with a step size of 1. All right, so I'm going to say, well, what's my slope there? I'm supposed to do 3 times the x plus 2 times the y plus 1. So that would be 2k plus 1. 3 times the x is 0 plus 2 times the y plus 1. I'm supposed to scoot over one whole thing. My delta y will be 2k plus 1. That's how far up I need to move. And my new point is going to be at 1 comma, and they told me 0, right? Boom. So that's my approximation is 0. What k will do that? Well, I'm working with the y values. I was at k. I went up 2k plus 1, so 3k plus 1. And my approximation ended up being 0. I'm using the same process up here, I just have an unknown now. So k is -1/3. And I'm done. So that was longer than I thought. I don't apologize though. I don't. I love you guys. You're so cool and super. And now you're going to go to AP Classroom and you're going to do an assignment that has 13 multiple choice. And it's not a test, it's an assignment. So if you get maybe 10 out of 13 and you would like to fix that, you just go ahead and go to your results and fix those 3 and send me a picture in Schoology. I'll just put a little assignment in there that says assignment fixed. So you should get 100% if you want it. Have a good one.